So then let's get started. Thank you very much for the introduction and welcome everyone to my talk about CPU load. CPU load? Really? Do we need to talk about CPU load? Don't we all know what we're talking about when we mention CPU load? I think we all have a very clear understanding of what we're talking about, right? Well, maybe you'll see that there are a few surprises and even pitfalls also related to CPU load. So I want to make sure that you're not going to step into these pitfalls, so let's get started. This is how the talk is structured. I'm going to start with a quick introduction, then talk about the CPU load and come up with a new idea talking about load. And finally, I'll then sum it up in a summary. So, introduction. First of all, what is load? Also here we have a very clear understanding, an idea of what we're talking about. So here, this is load. And where there's light, there is darkness. Where there's load, there is overload, right? And this is something you don't want, yeah? You want to avoid that. And in order to avoid this, you need to be able to, well, measure the load. Where are you today? Yeah. It doesn't help you if you identify low load and bam, you have a problem. That shouldn't happen. And some of the pictures you're going to see on the following slides I've taken from my book Embedded Software Timing, which is available in 5 languages. So those of you who read the book will see, okay, I've seen this in that picture. For example, this one about task states, which I introduce here. You know them anyway, right? These are the BCC, the OSEC and AUTOSAR classical BCC conformance class, task states, suspended, ready running, the transitions in between. With the extended conformance class, we have an additional task state waiting. And I want you to note the colors here, because I'm going to use these colors now to indicate task states over a time axis here, which is a very nice way to visualize runtime situations, right? So let me run you through the life cycle of this instance of task B here, gets activated here, starts here, gets preempted here by task A, then resumes, puts itself to sleep, so into waiting state. This low priority task then can execute. At some point the event it's waiting for a set, reschedule, resume, termination. So with this kind of visualization, you quite easily understand what's going on. And I also use it to define timing parameters, right? So for example, I'm not going to run through all of these parameters now. I'm just going to pick the ones which are relevant for the CPU load. To start with, it's the core execution time. So you can say the core execution time of this instance here of task B is the sum of all the running blocks. So all the dark green blocks summed up, their duration gives you the core execution time of this instance here of task B. Okay, later we'll also look at the net slack time, but let's keep that for a second aside. And now I come to talk about the CPU load as such. So first of all, the CPU load is the manager's darling, right? They just love it. Why do they love it? Well, it manages to compress scheduling, timing parameters, preemptions, interruptions, and all these ugly things into one single number, right? Simplicity. Yeah, manager asks, hey, where's the CPU load today? Oh, it's 85%. Oh, that's a bit high. Get it down by tomorrow evening. So, simplicity, right? What is it that managers love even more than simple numbers? Come on, any ideas? Well, traffic lights, right? Here, and there you go, you define your certain thresholds, your limits here, and there you go, you have the manager's super darling, the traffic light. Okay, so we're engineers, okay, we tend to smile upon this approach. However, I'd like you to stop for a minute and not smile at this approach. Let's actually try to find a definition, an implementation of the CPU load measurement that addresses this manager's expectation. And I'll tell you why. Just imagine you report to your manager something like, let's say, 69% on day one, right? Or one day. And then the next day you add a tiny little bit of functionality and bam, your system is overloaded. Well, then you're in trouble. How are you going to explain that to your manager? And later we'll see that this is actually quite a realistic setup. So, one side comment at this point here, AUTOSAR as of today doesn't really know CPU load, so there's no, there are the timing extensions, but they don't allow you to define the CPU load, which is maybe something we can and should add in the future. This is the way I define the CPU load. It's very simple, it's a fraction of 2 times. So let's first look at the TO, the denominator here. That's the duration of the observation. So it's the duration of some observation window. Okay? And what we then do is we check inside this observation window how much time was spent executing something else than the idle code. So we sum up the time the CPU was actually executing some productive code, some sensible stuff, right? You could also say we sum up the core execution times that fall into that observation window, right? Pretty straightforward, pretty simple. I'll give you one example here. So we have 3 tasks, A, B, and C. And then we introduce our observation frame, TO, here. And then we just count boxes, right? So let's do that. Our observation frame is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 boxes wide. And into these 12 boxes fall 1, 2, 3, 4, 5, 6, 7 boxes of execution, which means we observe CPU load here, 7 over 12, and that's roughly 58.3% CPU load, okay? The next step is also very obvious. We're not just going to have like one observation window and then run away and report that number. No, we're going to have subsequent observation frames. And that's shown on this slide here. So here you see the previous observation frame we had on the previous slide. And then the next one here, obviously some additional functionality kicked in, execution times went up, and so did the CPU load. And here everything's super relaxed down to 50%. Now, question. Which CPU load are you going to report to your manager now? Is it average? Maximum? Well, actually, we are building embedded systems, real-time embedded systems. And they should work in any case, also in the kind of worst case, right? So you should always, when building embedded systems, always think worst case. So definitely we're going to report the maximum in here. Okay, the average is also interesting because depending on the system setup, it identifies optimization potential quite nicely. So if you have a big gap between the average and the maximum, then, as I say, for some systems, this is an identification of some optimization potential. Right, that leaves us with one question now. Which observation frame should we pick, right? And to show you the impact of the observation frame, I'm going to show you 2 slides here, and I'm going to switch back and forth between the 2 slides. And so that you see I'm using exactly the same input. It's not just the same input data or something, it's really the same trace. Okay? And the only thing that's different is that here on this one, I'm using an observation frame of 50 milliseconds, whereas here on that one, that has a duration of 10 milliseconds. And just look at the impact on the CPU load. For the same system scenario, for the same data, we see in one case with a 50 millisecond CPU load of, 72%. And when we choose a smaller observation frame, we go up to 85%. Fantastic. I just gave you some material to cheat, right? So in the future, if you don't reach the CPU load defined by your customer, by your OEM, all you have to do is like expand your observation frame and you're going to get the CPU load down. Well, obviously, that's not what you should be doing. So let's move forwards towards the answer. Which observation frame should you pick? And for that, I'm yet coming up with another example here that has 4 tasks, a 4 millisecond task, 8 millisecond task, 60 millisecond task, and a 1000 millisecond task, 1 second task. So many systems actually do have a 1 second task for temperature measurement, for example, so it's absolutely realistic. And let's also assume now that this is like the execution pattern that we see, everything's fine, and then we see the load goes significantly up, right? And it really reaches a certain level that we even see a failed task activation here, meaning that this 60 millisecond task is actually due here again, but it's still running. So we see a failed task activation, also referred to as task overload. Now, side comment, what some projects then do as a workaround is that they say, oh yeah, we can accept that sometimes, so let's play around with the multiple task activations and increase that number a little bit and buffer the activation somehow and then later catch up with. Don't do that. It's actually a dirty hack, a dirty workaround if you do that. If it was up to me, the multiple task activations is one of the things I would kick out of the standard. I've never ever seen a sensible usage of multiple task activation. It's always been a dirty hack for an overloaded system, and instead of fixing the timing problems, they kind of work around, right? But that's just a side comment. Let's now talk about the CPU load again and the observation frame. So I'm now showing you the different CPU loads for different observation frames. I'm going to start with quite commonly used observation frame, which is the super period of your system, meaning the period with which the activation pattern then repeats. So here in this case, 1000 cannot be divided by 16, but 2000 can. So TO equals 2 seconds. Let's go for that one. And we calculate a CPU load of 69.15%. So that's exactly the example I gave at the beginning, where you report a 69% to your manager, but already your system has a local hotspot. It is overloaded. You already have a timing problem, and you report 69%, which you will remember the traffic light corresponds to a green traffic light. So that shouldn't happen, right? Let's look at the most commonly used observation frame, which is the period of the slowest task. So the slowest task is here 1 second, right? And the idea behind this approach is that, yeah, in my observation frame, I see every task at least once. I don't know what that shall give you. In the end, it doesn't give you anything. As you will see here, again, we report a green traffic light, 69%. Right, and now I'm iterating here through the different periods. So let's go for TO. 16 milliseconds. So for this runtime situation already, we get 3 observation frames. This one here with 75%, this one here 68.8%, and this one here with oh, look at that. This one reports 100%. So that's good. I mean, it's not good that it's overloaded, but it's good that we report the overload. We report a CPU load now of 100% for a system that actually is overloaded. And that's good. Same for 8 milliseconds. So here also we get twice as many observation frames, obviously, and we report 100%. If we then choose observation frames which are even smaller, at some point, it doesn't make really sense anymore. We're starting to report false positives. So here we report 100% where there's no problem whatsoever. Okay, and then it just at some point becomes digital, where we just alternate between 100 and 0%. Doesn't give you any information at all anymore. Right, so back to the question, which observation frame should you pick? Okay, so the problem is, unfortunately, there's no silver bullet, right? So there's no such thing. However, I think with the topics we just discussed in the back of your mind and the knowledge about your project, you should be able to pick a sensible, a correct, good observation frame, right? Very often, it's actually the main control loop, if there's such a thing in your ECU. The main control loop is a pretty good starting point. And then typically you will end up with values between 10 and 50 milliseconds probably. If it becomes much bigger, then I would question whether that makes sense. If it's much smaller, maybe it's a bit too critical. So this is, according to my experience here, a range for a sensible TO. Okay, now let's talk about what I like to name task load. So, and to get there, let's take a look at the previous picture. Okay, I just sold you something. I just sold you a very nice approach with a TO 60 milliseconds, and you bought it, right? Actually, I was lying a little bit to you, because look, if we use the same TO of 60 milliseconds, but now just shift the observation frame a little bit, for the same scenario, we are back to our original problem that we're not reporting 100%. Okay, so I wasn't quite honest to you. But that's a real problem. And I thought about how can we address it? How can we actually solve this problem? And while thinking about the problem, I realized, well, actually, to some extent, the CPU load is a little bit like averaging, right? You have, in the end, it's the processor itself, at any point in time, is either executing the idle loop or not executing the idle loop. So it's a digital decision, and based on that, now for a given time frame, you calculate the CPU load. So it's got to do very much with averaging. So I picked the averaging figure from my book, where I just outline here 12 values, some random values here, and talk about different kinds of averages. So there's the overall average, that's very straightforward. Then we have the intermediate average here. So we do build these groups, and at the end of one, we start with the next one. And then we have this, I call it moving or sliding average, right? And this is the one we've been using previously with the observation frames, okay? And could that be a possible alternative, maybe? Actually, it doesn't look too bad, because here, as you can see, at least if we're now looking at the max values we report here, we really get a bigger value here compared to this approach, right? There's only one problem with this approach, is if you really were to implement that, let's say, for example, on the ECU, it's going to be very costly. And, well, embedded software resources are expensive. We don't want to waste them. So maybe there is another approach, a better approach. And that gets us to the task load, which is based on the NST, the net slack time. So let's do a recap. So you've seen that picture here, and I highlighted the net slack time. So I need to briefly explain what the net slack time is. It's based on the slack time, which is kind of the size of the gap here. So from termination all the way to activation here, the slack time itself, okay? But this is not a good indicator for headroom, because as you can see here, this task A execution falls into this gap, into the slack time, and steals time from your potential headroom, right? And this is exactly what now the net slack time is about. It takes the slack time and deducts all the core execution times of tasks with a higher priority. Okay? And then the net slack time obviously is calculated for all the tasks. So in this diagram, it shows the net slack time for task B, but we could do the same now for task C, for task A, and so forth. So each task comes with a net slack time. Right. And now the idea. So the net slack time, as I said, is a nice indicator for headroom of this task. Okay? So if there's no more headroom, so if the net slack time equals to 0, then the task is overloaded, you could say, right? The unit of the net slack time obviously is seconds, or milliseconds, microseconds, nanoseconds, whatever. And that's not quite a good fit for load, right? Seconds, doesn't fit. So how about normalizing it? with obviously another time to get a unitless result. Any idea what we could use to normalize the task period? 100 points, exactly, the task period. That's a very good idea. So, and then we get our task load. So here we subtract the net slack time from the period, and that is kind of the time used up. So I'm flipping the logic round. I'm not talking about headroom now. I'm talking about how much, because I want to talk about load, right? So how much time uses it up, and that's this value here. And then we normalize it with a period. Then some transformation gives us this term, which then I say is the task load for this task here. Okay, so now a more formal definition, if you like. So each pair of subsequent occurrences of task T results in a net slack time for this task T, right? Then the task load of the task load NT of each task T would then obviously be the possible or observed maximum, again, of the NST, right? So it's the same approach we took earlier for the observation frames. We reported always the maximum, and now here we observe several net slack times or task loads. So again, let's pick the maximum because we think worst case. And then obviously we said that already. You have as many net slack time, as many task loads as you have tasks in the system. So the definition then would be to report as the overall load, the task load of the system now, the task load n of a system with q periodical tasks would be the maximum among all the tasks. So it's like a two-dimensional thing. Each task comes with a number of task loads, and you pick the maximum here, and then among all the tasks you pick the maximum again, right? And that would be then the task load. What about non-periodic tasks and interrupts? I'm very honest to you, I don't know. We would need to think about it, and maybe you've got a very cool idea, and if you have, let's have a discussion on this. Okay, so let's come to the summary. People tend to think it is very obvious what CPU load means. I hope I could show you a little bit that it's slightly more complicated than that, and that also I can say the different definitions and the different understandings lead to real problems in real projects. So I mean, as I mentioned yesterday in the 1-minute pitch, we do a lot of firefighting task forces and so forth, and very often we join task forces where they say like, the load is not too bad, but then it's horribly overloaded, right? This is a real problem. My suggestion would be, and that's now the maximum of the maximum of the maximum, if you like, we could define the load, really the system load, as the maximum. As the maximum of the CPU load and the task load. You could even think about combining that. Yeah, just an idea. Okay, whatever load definition you pick, thinking about this topic at all and thinking about the details, I think already helps improving the software quality, because you think timing, you think real time, and that is a very good thing. Don't just look at the functionality of software, also consider the timing, and that will save task forces, headaches, and long weekends. And with that, I come to the end of my talk, and I'm open for questions, comments, and discussion. Thank you very much.